No? Okay, so yes, oh. It's strange when you hear your voice. Yeah, can I? Yes, okay. So thanks to the organizers for inviting me to give this small course about qualitative theory of dynamical systems. Okay, so the purpose is just give some mathematical background. So I think that you already know everything here, but I hope that it will be useful also for mathematicians just to recall things and to have some history. Okay, story, sorry. Yeah, as you see, my English is like this, so I apologize for that. Okay, so just let's start from the beginning. Yeah, the beginning is that you have, oh, come on. Can I? Oh, here, yes. The stars is just x dot, which means the derivative with respect to t of some x, sorry, equal to something. Yes, and this something is a vector field. That means that x is a function defined in some open set in Rn to Rn. Yes, and x, of course, is Rn. And here the mathematicians that do these things in ordinary differential equations and dynamical systems always have this, how to say, this strange notation if you want, because sometimes x, sorry, is a point, yeah, and sometimes x is a function, okay? So in this case, what we want is just study, study the solutions. That means x as a function. Okay, of t going to x. Yes, but sometimes when we draw things in what means the phase portrait, which in this case is Rn, we just say x as a point or x as a curve or whatever. Yeah. Okay. So the thing that the qualitative theory wants to study the behavior of the set of all the solutions. Not only one, two, all the solutions. Okay? And the thing is that, as you already know, sure, the solutions cannot be explicitly computed. So without computing the solutions, we want to study how is the behavior, okay? Without computing. Okay? Yeah? So the first thing, the first important result, let me say the first important result what do you think that is the main result? The existence and uniqueness result. Huh? Existence and uniqueness result. Okay? This is the first one. Let's say that if you have, this is Rn, 1, x, 0, says that with some conditions about X, then you have only one solution. Okay? Only one. And these conditions is X has to be Lipschitz. Yeah? Everybody knows what means Lipschitz? Yes or not? That's something like. Okay? If you don't like this notation, that means norm with one. Any norm that you want. Okay? So this is the first one. And now we think, okay. Oh, come on. I can't believe it. Okay. No, sorry. So once we already know that we have a solution. Okay, see that this is a remark. Usually, we don't know where the solution is defined. That means that this X solution is defined in some interval. But this interval can and does depend on the initial condition. Okay, so sometimes you have that this interval is the full R space or T positive or T negative or whatever. Okay, but in dynamical systems, we consider the solutions, the vector fields that have solutions that are defined for all T. Okay, so we don't have to care about this definition domain. Yes? Okay, so now we think, okay, we don't have no idea about this vector field. We know that there are lots of vector fields that we cannot give the explicit solution. So what can we do? Yeah. So the first thing that we can do is just study this local behavior. Okay, that might explain and say lots of things about this local behavior. So we'll start now for the beginning of this local behavior. Okay, so local behavior, what means is the behavior of the solutions in a neighborhood of a point. Okay, so we take a point P in U, and we ask if we can know something about the behavior of the solutions around this point. Yeah? So have this P, and we only are worried about what happens here. Yeah? We don't care about what happens outside of this small neighborhood. Yeah. So if we are doing things about, in a neighborhood of a point, the first thing that we can think is that, okay, so take my vector field and do Taylor. Because Taylor is, well, the theorem to study things around something. So we take Taylor. This is the differential, the Jacobian matrix, multiplied by x minus p, plus something that is of order quadratic. Okay, that we think something like this. So let me just write this. We understand that means norm. Yeah? Okay, so we think in this. And here we see the first difference between a point that has this value equal to 0, so it's a singular point, an equilibrium point. And if the point has this vector not different from 0, then we have a difference here. This is constant, this is not constant, this is linear. Yeah? So what do you think that is more general, to have singular points or don't have singular points? The more general thing is don't have singular points. So the first thing that we have to assume is that xp is different from 0, because be different from 0 is a generic condition. Yeah? Usually the things are different from 0. So if you have that the vector field is not 0 in a point, then we say that P is a regular point. And we have a result that says something that, the question is the dynamics of the full similar because if Taylor is a good theorem, so it seems that this has to be true. Yeah. And also I want to say what means this similar. Okay. The similar word in maths means something like you can construct a change of variables that you can see your system in this way. Okay, you think x is equal to hy, sorry, and then y dot is this one. Okay, this is a change of variable. That means similar. That in a mathematical terminology means to be topologically conjugated. Okay, so I am writing this. So let me just, what means similar means in fact, the topologically word here is not extremely necessary. You can think here in CR conjugated, analytically conjugated, any regularity that you want. Okay, and the definition is that x and y are topologically conjugated, CR conjugated, if there exists H from some neighborhood to another neighborhood, and homeomorphism this is a really mathematical word. Homeomorphism means that it's continuous, is invertible, and the inverse is also continuous. Okay, so you can go in one direction and in another direction in the same way. Yeah? Sorry, this is x to y. Such that, and the thing is that I cannot remember exactly the formula, but I don't need to remember because the only thing that I can need is that this is a change of variables. Okay, so I write this one. This is the gradient or the derivative, sorry, the differential function. There's a common function, x dot. This is x, sorry. I always do this in the thing that I don't want. Let me just think in this one. It's better. Sorry. It's better in this way. You will see now. Because now I can substitute here. X is just it's a change of variables. So for any x, I have one y and only one. Yeah. So the thing that I want is that the vector field for y is equal to this one, because in this way it's a change of variable. No? So what we want is this. Okay, that means to be conjugated. Depending if these open sets here, U and B, are global or local, we have a global conjugation or we have a local conjugation. Usually we have local conjugations because we cannot define a global conjugation usually. Okay, so if this neighborhood here, if this open set is a neighborhood of some P, and this is a neighborhood of some Q, okay, we have a local conjugation between these vector fields. Okay, and see that this is a way to classify the vector fields. Okay, so we only need to see which are the different vector fields that are conjugated between them. Okay. Okay. So the thing now, this similar, okay, means sorry, yes. If this homeomorphism is differentiable CR times, and the inverse is also CR times differentiable, then we have a diffeomorphism. Say CR diffeomorphism, whatever you want. Okay, the word here is about the regularity of the change of variables. Okay, so around a regular point. Around a regular point, we have this flow box theorem. You know it? You know this theorem? No? Okay. So this is, in fact, maybe more important than the linearized result, because almost every point is regular. So this results say that if you have a vector field and a regular point, okay, then it is locally and I mean around P, okay? So this U is a neighborhood of P, then it's locally conjugated to, and this is the amazing thing, this one. To a constant vector. The important thing is that it's a constant vector. It's not important that you have here 1, 0, 0, 0. Don't care. It's a constant vector, in particular XP, if you want. Okay? So that means, see?
Is an homeomorphism always differentiable?
Yeah.
Okay. Sorry for the stupid question.
No problem. No, sorry. An homeomorphism is not differentiable. Okay, yes, and I differentiate, I know, because it's easy. If not, I have to define flows and so on. Yes, you can think in detail if you want.
Normally we use
if not, the thing is that the flow of one vector field is going to the flow of the other vector field. But then I think I have to talk about flows and so on. So.
Okay.
Yes.
Thank you.
But good eye.
Yes, I was.
Yeah, sure. Okay, so it's conjugated to this one. So that means that you have a point here, P, and then you have some neighborhood, that's this way, for instance. Okay, so the solutions here are like this way, for instance. And we know that because this system is conjugated to this one. And here you have the origin. Okay? And then you have here the conjugation. Or H here and H by. Yes? So in here you have this situation because you know that this system in a neighborhood of this regular point is conjugated to this one. Okay? Which is a really easy system. Okay? So see that in this case, this is not such innocent as it seems, because these functions, y2, y3, 1, yn, are first integrals. So that means that the system is integrable, like a Hamiltonian system with lots of independent integrals. Yeah, but only locally, yes, of course. But at the end, what you have is that in a neighborhood of a regular point, all the vector fields are integrable. Okay? Always locally. So everything is said in this case. Local behavior around a regular point, we are done. Yeah? So this is why when you study a system, you always look for singular points. Okay? Because the regular points are done. Okay? So now singular points. Okay? So what happens? If this is 0, so we have a singular point. So here, remember that what we have is that x of x, yeah, is the differential matrix multiplied by this one. Okay, so think that if the point is regular, we are really lucky because we don't have any exception, we don't have anything. If the point is regular, always you have the conjugacy given by the Box theorem. And now the natural question is, okay, if you have a singular point, then what happens? Can I skip this or not? No? And the answer, as you know, is that usually you can. Yeah? And you have this theorem. That is, the answer is Harman, that say that if you have this vector field with xp equal to 0, and the matrix satisfies some condition that is to be hyperbolic, that is, just to recall, the spectrum as the eigenvalues, sorry, is contained in real of lambda different from 0. Yes? Always real of lambda different from 0. Okay? So in this case, then the system is topologically conjugated to the linear part. Okay.
We say that it's topologically equivalent.
No, topologically means that the H there is an homeomorphism. So the thing that you have solutions is going at two solutions. Okay. Yes? Only this. And this is, there is no way to improve this. Okay, so I could, I can do the naive definition that I give in this case, in that case, sorry. This is more complicated, but the thing is that if you go further, then you see the same. Okay? It's like this. So that means that in this case, what we have is that in a fixed point, so for instance, think that, sorry, you have here a point, P, okay? So let me just in R2. And then you have here something like this. This is a going direction, and this is going out directions. For instance, this is a saddle. Okay, I really remember all the behaviors after. Okay, so if you have one situation like this, then you have something like this, and like this, and like this, and like this. And you know that because of this theorem, because you know that this situation here is the same as the linear part. Okay, so the linear part For instance, you have a linear saddle. So, okay? And you go from here to here by means of homeomorphism. Okay? So just to recall the behaviors, yeah? In the planar case, okay? In the planar case, just recall planar case, that means X. Sorry. Sorry. A matrix. 2 times 2, yeah? The system is completely understood because you can give all the solutions. Okay, so you have these pictures that are already known, but you can have something like this. And that means that you have that eigenvalues of A are lambda and mu. Okay, if you have lambda positive, lambda multiplied by mu negative, yeah, then you have a saddle. If you have positives, you have a node, and in this case it's a repeller because everything is going out. Yes. I didn't see anything about the eigenvectors.
It's a semicolon or it's a product?
It's a product. Sorry. One is positive and the other one is negative. A column. Yes. No. Sorry. Everything is, one is positive and the other one is negative. Here you have both of the same thing, yeah, positives. And you have, for instance, something like this. Okay, you can have something like this, or something like this, or everything in straight lines, whatever. Okay, this is a repeller. Then you can have also an attractor. Okay. This is with respect to real eigenvalues. And if you have some complex eigenvalues, then we can have lambda is this one conjugated because you are in the real case. And then what you can have is that if the real part of lambda is different from 0 and positive, then you have repulsion, focus. Okay? If the real part is negative, you have an attractor, sorry. And also you can have real of lambda equal to 0, but the value is not 0. Lambda different from 0, and then you have asymptotically. Okay? And if you want to do the exercise to see what happens when you have lambda equal to 0, feel free. Okay? Yes? So the linear maps, at least in R2, are completely understood, and also in Rn because you have the explicit solution. Okay, so let me just say something math freaky, yeah, that you can have systems that are not defined in R or R2, Rn. You can have systems defined in, for instance, the circle. Okay, so I know that I don't say anything about maths, but I know that you know about maths. So let me just think in this map. Okay, just this is a curiosity. Okay, so if you have this map, and then S1 is just 0, 1 with 0 and 1 equal, identify it. Yeah. And then think in this linear map, which is this one. Okay, this is a linear map. This linear map is chaotic. Chaotic in the mathematical sense. I mean, everything happens here. Yeah, so this map is chaotic and it's linear. Yeah. And we have also another example, also in the torus, that Jose knows that. This F in the torus. Okay, you know the torus is a donut. Yeah. So, which is also linear. This is the Arnold cat map that I like very much. And then for any x in here, which is two angles, yeah, you have the latitude and the longitude in the torus. And then here you think in this map, okay? And this map is also, well, has a strange behavior. Okay, it's not easy. It's topologically transitive, has periodic dense orbits, has a dense orbit, so it's also chaotic. Okay, if I have time, I will return to this map sometime. Okay, so linear maps are easy, yes, but can exhibit also complicated behavior. If you think in linear maps in other manifolds, in other sets that are not the plane. Okay? So just let's end the freaky part. So I lost. Yes. So, okay, we have this theorem for some type of singular points. And what happened if the real part is equal to 0? Yeah. And first, we say, okay, let me check if there is some choice, some possibility of have similar result as the one for the hyperbolic singular points. And the answer is, of course, not. Yeah, because, for instance, see x dot is 1. Then what you have here, this is an F. Yeah, we think in the linear, in the real line. Yeah, you have here the equilibrium point, and since the derivative with respect to the independent variable is positive, always, what you have is the arrow, you are always growing. So here you go in this direction, and here you go in this other direction. Yeah, but if you have this one, which is also eigenvalue equal to 0. Yeah? So, and here you have that for x being positive, you have that you grow. And for x being negative, you decrease. So you have this one. So these are two different qualitative behavior. So there is no way to characterize anything that have this real part of lambda equal to 0 by the linear part. Okay, so we have to study more further. Yeah? So since we see that here we have lots of work to do, then we think if it's necessary. Because if not, come on. Yeah? And the thing is that why are these points important? Why are the non-hyperbolic points important? Yeah. So usually, if you have a system, the generic thing is to be regular. Okay? But if you think in to be singular, the generic thing is to be hyperbolic. Okay? Because to be different from 0 is always the generic thing. But if you have a system with some parameter, as you know really well, better than me because you work with bifurcations hard, you know that if you have a family, it is generic to encounter values of the parameter such that the fixed point is non-hyperbolic. That are really the interesting points because it's the step through go to stability to instability to have 1 point or to have 3 or whatever. So it's important because in this situation, which is in fact the real situation because anything in the nature has parameters, yeah? Then these fixed points are generic. So it's important to study these fixed points, to know about the stability, to know about what happens. Okay? So just to recall, let me just write some of the easy and basic bifurcations. Yeah, that in this way we remember everything and we know everything. Okay, so sorry, and here the bifurcation parameter. That's non-hyperbolic just to summarize. Yeah. Okay, so which are these bifurcations? The first one is the saddle norm, which is this one. Yeah. And see what happened here. Just I know that you already know this. You already know this more or yes, no? Yes. So the fixed points here are 1 if mu is equal to 0, 2 if mu is positive, and 0 if mu is negative. So here you have this bifurcation diagram. In here you have 2. Okay. So if mu is negative, everything is negative. So this is x. Yes. So we are decreasing. So anything here is like this. For x for mu equal to 0, what we have is this one. Yeah. So everything is decreasing also, but here we have this fixed point. So the thing is that if you are here, you are going down until minus infinity, but here not. If you are here, then you are going to 0. Yes? And in this situation, what we have is that this one, okay? So just for see easily, in this, from here to here, you have always the matrixing. So pick x equal to 0, you have mu positive, so you are here going down, yes? And then you have to complete with the other arrows. It's like this. So in here, you have that 0 fixed points, 1, 2, okay? And this is the bifurcation. No? Change of the behavior. That means a bifurcation. Change of the behavior. Okay? Always, doesn't matter how close are you from the origin, that you will always find this behavior. Yeah? Okay. And you have also other bifurcations like the transcritical, pitchfork. Just let me draw some pictures here. Pitchfork. This one. In here, what we have is that 0 is always a fixed point. But when mu is negative, is an attractor. This is x, remember, yeah? This is mu. Mu is a parameter, so it's fixed. No? When mu is 0, what you have is a degenerated saddle. Yeah? And in this case, sorry, it's not a degenerated saddle. It's an attractor. Okay, that's it. Yes. And for mu positive, you still have this 0, but change the stability, and then you complete. No? Okay. And this is the bifurcation. It's also a change of the behavior. So you have not only that it appears 2 more fixed points, but also change the stability of the other fixed point that is maintained along all the bifurcation. The transcritical. This is phi is one. You can see that I cannot remember. It's impossible. I try along the years, but I cannot. So in this case, what we have is that you have also this 0 as a fixed point. And also you have x equal to mu, equal to, is also a fixed point here. So you always have the same number of fixed points. But here, what you have is a change of the stability. When mu is positive, x equal to 0 is a repulsor. When mu is negative, it's a attractor. Okay, and you can see easily that in the case that mu is negative, this is a repulsor, and this one is an attractor. This one means transcritical. Yeah? Change the character of the critical point. Okay? Yes, these are the ones in R. And you have only one more in R2. Well, you have plenty of bifurcations. There are plenty of bifurcations, but maybe one that is also well known is the Hopf bifurcation. Okay, so let me just write, which is this bifurcation, and I will stop in doing this. Okay, so the last one is the Hopf bifurcation. So I, sorry, write in polar coordinates. Everybody is familiar with these coordinates, so it's more easy to understand. So in polar coordinates, you have r dot okay. Okay. And this guy here, negative. If not, it's the same, but in the opposite side. Okay. So see the thing that you are here in polar coordinates, but here you have a saddle node. Yes. Here, this is a saddle node. If you only think in R, yeah, this is a saddle node. Yes. And think that in the saddle node, what you have is that you have two fixed points and so on. So the only thing that we need to think in here is just that we have to add this one. So a fixed point here is a periodic orbit because you add the angle. Yes.
Isn't a hint for bifurcation in the case of just the first equation?
Yes, sorry. Yes, this one. Yes. Thank you. No problem. You're right. Absolutely right. Yes. Okay. But anyway, the case is that if you have here a fixed point in R, you have the angle, so you have a periodic orbit. Yeah. So what happens here is that you have this R equal to 0 in polar coordinates. It's not exactly a good thing to do because the polar change of coordinates is not well defined, but in this case also works. So you have always the origin as a fixed point, yeah, and two periodic orbits when mu is positive because alpha is negative. So the thing here is that you have this axis always as a fixed point. Here you have 0, okay, and then here appears something like this, like the pitchfork, yes, but you have to think also in the angle, yeah, okay. So and here what we have also is the same. If mu is negative, this is an attractor. Everything is going to the origin, and here, but not in this way because it's how to say, it's a focus. So it's like this. Here you have a repeller, and everything in here is going to the periodic orbit. The periodic orbit are attractor. Okay. 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 So I don't know how much time I have. Is just a half. Okay. So then, since we see that these fixed points having this real part equal to 0 are important, then we are trying to get some tools to study. Okay, and maybe the one of the tools, maybe the most known tool, is the Lyapunov functions. You know about the Lyapunov functions? Lyapunov functions? No? What? I did it sometimes. Okay, so let's explain these Lyapunov functions. Okay. And this is now thinking, how to say, we start with this local behavior, yeah? And now we also want to go to local behavior because we want to study what happens around these critical points that are not hyperbolic. But we're interested in what happens in a long-term behavior. Yeah. So now let me explain things about this long-term behavior, and then in the middle we will see this Lyapunov functions. That means the following. What can we say about the limit of this is the first question, okay? And the first thing that we can try to understand is what means to be stable for a non-hyperbolic fixed point, okay? So this is the Lyapunov stability, which is the stability. Yeah, you can draw this Lyapunov, okay? And the other thing that we can say that I don't know if I think that I don't have time to today is just see if there is some solutions of the system that when the time goes to infinity or to minus infinity, go to a fixed point, because in this case, it's also a local behavior. And at least it's something, okay? But first this, yes? So let me just draw what means to be stable and what means to be asymptotically stable, because we have here two definitions, okay? If you always say, see the linear part, usually what you see is just the asymptotically stable, okay? But there is another definition, which is to be stable, okay? So the first definition is to be stable, okay? And this definition means that P, a singular point, is stable if, and let me write the mathematical definition, and then I draw something, okay? If for any neighborhood of P, this is a usual notation. When I say this, I mean a neighborhood of this fixed point, okay? There exists another neighborhood such that if an initial condition belongs to B, then the solution of this going through this point satisfies two conditions. And that means the flow of the solution sorry. Yeah, everybody, yes, so you have this existence and unicity result, you have a unique solution on P, on Q, sorry, and then you denote this solution by this, okay? That's it. Satisfies first that it is finite for all T positive. This is a general result about ordinary differential equations. So you don't assume that the system has the solutions defined for all T. And phi the T of Q belongs to U. Okay? And here the order is sort of important. So see what we are saying. You have here a point P, okay? You take a neighborhood, any neighborhood U. Okay. And then the stability conditions say that, okay, any solutions that starts in a more narrow neighborhood, B, can go out of B, but cannot go out of U. Okay? That means stability.
A question. The second condition is for positive prime.
Yes. Yes.
Thank you.
Yes. Yes. I'm lucky to have you. Okay?
It was clear for
Yeah, but no, but it's perfect that you say me this because I always forget about these things. Okay, so this is the stability condition. That see that if you have a system and you linearize around a fixed point, then you cannot have this one. Okay, I will write this, but you cannot because everything is going into the fixed point. Yeah, so you have this, but you have more than this. This is a weak condition about the linear stability. This is what I want to say. And then we have the asymptotically stable condition. Again, you have P, xp equal to 0, and then you say that is asymptotically stable. Yeah, if. And the first thing is that it has to be stable. Yeah. And the second condition is that there exists another neighborhood, okay, such that for all initial condition that belongs to this new neighborhood, then the solutions goes to the fixed point. Okay. Yeah, and see that you need this also, because you can have pathological situations such that, for instance, you have here a point P, and then you have that everything is like this. And you can have it this one. And this point is not stable, of course. Yeah? But all the solutions go to the fixed point. Yeah? So you need both. Okay, so these are the definitions. And which are the results? The first result is the linear stability, the result that you already know, but let me just say some words about it. So this is the linear stability result that is a straightforward consequence of Harman theorem. Yeah, let's say that if you have a singular point such that the eigenvalues of the differential matrix have all of them real part negative, then the fixed point is asymptotically stable because it's conjugated to the linear part and so on. Okay? And sorry, I forgot one definition. I'm sorry, unstable. Okay. And of course, you have this stability result, and you have also the instability result, that is, if there exists one eigenvalue with real part positive, then P is unstable. Okay? Just as a corollary of the definition and the Harman theorem. And now, okay, we remember that we are thinking in these fixed points having the real part equal to 0. So we need to answer this question. And this is when Lyapunov functions enter in the scene. Okay. So let me just, yes, I think, yes. Lyapunov function. Okay. So, sorry. Okay. First, I define what I want to I define what means this Lyapunov function, and after I will give the result. Yes. So, which is a Lyapunov function? A Lyapunov function is associated to a point. Yeah. So imagine that you have this one, and that you have a fixed point P equal to 0. Okay. So a Lyapunov function is a function, first, a function that is defined in a neighborhood of the fixed point. Okay. And going to R with this is our notation. Yes. It's a real function. Okay. That satisfies first that it is positive for any x belonging to P, to the neighborhood, sorry, except by the point. Okay, and in the point is 0. Okay. And the second one is like this. How can we denote the scalar product? Okay, I denote the scalar product by a dot. Okay. Like this. Yes, and that means this is the gradient, because remember that H is a function, it's a real function. So it has n components, so this is the gradient. So it's a row vector. Yes, and this is the vector field that is a column vector. So this is well defined, there is a number. And this has to be negative for all x in the neighborhood. Yeah. And this is a Lyapunov function. That's it. And we have also the other definition, that is an strict Lyapunov function. Let me, instead of points, see this. Change the second item by this one. Okay. Yes? I think what means this? I mean, just a picture to clarify a little bit. Yes. If in this point, this is 0, this is positive, so you can think that it's a closed curve. Yeah. And think, for instance, in this one. It's easier to understand in this. Yes. What means this? Which is the geometrical interpretation of the gradient. This is not a rhetorical question. The geometrical interpretation of, imagine that you have this one, yes, positive, and you are drawing this, yes? Imagine that you have this situation, okay? I don't want to enter if this is a closed curve or not, yes? Imagine that you have this, and this is the contour plot of this curve, of this superface, if you are in more dimensions, yeah? And then, which means this.
The direction of the steepest descent of the curve, where it goes down the quickest.
Is the normal. You have two vectors, yes? Well, sorry, two spaces, if you want. Yeah, I always think in the plane, but this is general, but thinking in the plane, yes? If you think in the plane, this is a curve, yes? If this is a curve, you have two vectors, the normal and the perpendicular one, yes? Then imagine I don't have this direction, okay? So the gradient is the normal, no? So here you have the normal and the tangent, yes? And think now what means this? This is a scalar product, yes? And when you think, I don't know, maybe in the school, but I don't know, the scalar product of two vectors, yeah, is the norm of 1 multiplied by the cosinus of the angle. Yeah. So to be negative means that this cosinus is negative. So that means that this vector is going in this direction. Yeah. Out of the tangent, below to the tangent. I don't know. Yes. So, and this vector here is the vector field. Yes. So you have that in this curve, and let me just draw this. In this curve, the vector field go into the this region. Okay. So now think in the solutions. Okay. If you have a solution of a vector field, okay, if the derivative has to be the vector field, that means that the vector field is tangent to the curve. Yeah. So if the vector field is tangent to the curve, if you are in, you cannot go out, because the vector field is going into this region. Okay, so you stay here. So you are stable. Okay. This is the geometrical interpretation, well, more or less, of this condition. Okay. So, which is the result? Yes? the result is that this theorem if you have a vector field and you have a singular point, and then assume that there exists a Lyapunov function for P. Okay? Then, if there exists this Lyapunov function for P, P is stable. Okay? And if there exists a strict Lyapunov function for P, then P is asymptotically stable. And that's it. It's really easy. Okay, we are done. We don't have any problems, blah, blah, blah. But as so many times happens, this sentence here, if there exists. So you have to find this function. And this usually is not easy to do. Okay, so we don't have any problem solved. Okay, we only have another tool. Okay, so let me check the time, and if I can give you some example. Well, okay, so let me just say some example, and we will come into this tomorrow. Yes. Or better, I write the systems and you find the Lyapunov function. Yes? Okay. Samples. Exercise. Okay. This one. Well, I need my glasses, because I don't distinguish if I have x power 3, x power 5, or whatever. Okay. Okay, this one. C. Okay. Okay, if you lost more than 15 minutes or 20 minutes, think that maybe I am wrong. Okay, because I can do some computations and okay. So don't be crazy if you don't get that result. Yes. And the other one. Is stable. Mm-hmm. Okay. Okay. So I think that I can stop here. Yes, because it's too much. So the thing is that, well, let me just say a corollary, which is really nice. I like more. So there is a corollary of this theorem that is really, really useful. With the, I mean, if you have to deal with Lyapunov function and you see that the origin or the whatever, the fixed point is asymptotically stable, but you cannot get any Lyapunov strict function, then you go crazy because you have to add some terms and then it's not positive and so on. But there is a result that is really useful to help us with these cases, okay? And the thing is that if the set that the strict condition is not satisfied, yes? So you have this x and you have some x such that this is 0, okay? But if this set does not contain any solution of the system except the fixed point, which is a solution, then it's asymptotically stable. Okay? Then it is asymptotically stable. Okay? And see that this is not really so hard to see, because the only thing that you need to see is that this set is not invariant. Okay? So this is not so hard to see. It's better to see this condition than try to find a strict Lyapunov function. Trust me. Okay, so if you want, you can do the test, because this point is really asymptotically stable. So if you apply this result, you will see that is asymptotically stable. Okay? But okay, try to find a Lyapunov strict function for this, this vector field. Is harder. Okay. Okay. So that's it. Any question? Next day, I will try to make an example with log about terra, because this is a mathematical biological congress, so log about terra has to appear. Okay, and that's it. Yes. Any question? No. Okay. So thank you.
Thank you.